Hello and welcome to the presentation of our paper entitled Image Generation for Efficient Neural Network Training in Autonomous Drone Racing, presented by the Artificial Intelligence in Robotics Lab of Aarhus University and the Nanyang Technical University of Singapore. First of all, what is drone racing? As you can see on the video on the right, drone racing is a sport where human pilots fly drones at very high speeds using FPV goggles, as in first-person view, on a track that is filled with obstacles and gates to cross. And it is a very fast-paced game where reaction times is very quick. What interests us here is autonomous drone racing. It is the same sport except that we replace human pilots with a complete software solution. The robotics paradigm is composed of 3 blocks: sensing, planning, and acting, and many complex challenges of autonomous drone racing can be seen in those blocks. For example, in the sensing part, there is image recognition and object detection challenges. In planning, we can see localization and mapping or trajectory planning. And in acting, it's all about control and UAV dynamics. Our solution focuses on the perception block of drone racing. The motivation lies in the fact that recording and annotating a custom dataset for machine learning-based models is a very tedious task and requires a lot of hours of human labeling. Researchers have different needs in terms of data, meaning that using a publicly available dataset is not always feasible because researchers can need different sorts of ground truth annotations. And achieving generalization requires humongous quantities of data and labeled data most of the time, so this is not always feasible. What we propose is a hybrid dataset generation pipeline that takes advantage of a motion capture system to automate large-scale annotated image generation to provide more generalization capability to the model while making the problem simpler. The idea is to generate a synthetic view of the scene, of a random scene composed of 3D models, which is overlaid on top of a real background image, thus giving it a very realistic feel. The pros are that we can use any obstacles of any shapes and any colors since we just need a 3D rendering software. And using modern rendering techniques, we can obtain a very realistic scene. It also gives us the possibility to have infinite amounts of racing tracks and a near optimal generalization potential thanks to that. The biggest limit, however, is that we are restricted to the background environment because we use a motion capture system and thus we cannot use outdoor images, for instance. The pipeline can be decomposed in several steps, and the first one is to pick a random background image from our dataset of base images that comprise no elements but that are annotated with the 3D pose of the drone. To generate such dataset, we used the motion capture system and flown a drone manually, and we recorded the 3D pose of the camera at every frame. So we can obtain the extrinsic parameters of the camera to model them in our virtual scene. Furthermore, we need to model the camera. This is done only once, but it allows us to extract the intrinsic parameters of the camera in order to replicate it in our virtual scene. With those parameters, we can create the projection mapping, which then gives us the possibility to create the same perspective. And if we had distortion on our actual lens, we could replicate it in our virtual camera. Then we can spawn many elements from a collection of obstacles or gates, for example, and we can apply random rotations and translations to each of those elements. Finally, we can render the scene and use transparency in the background in order to overlap it on top of our real image. We can take advantage of this method to generate any sort of annotations that we would like, for example, the center of the gate, the bounding box of the gate, the orientation towards the camera, or the distance with respect to the camera. Once we computed all these annotations, we can overlay the render image on top of the background image. Here we kept the annotations, such as the perspective grid, to show you that the perspective matches quite well. This video shows the whole pipeline as an animation. So you can see that we can randomly translate and rotate any elements as we would like, and then compute annotations for each of them. We can also alter the image to replicate the noise and the motion blur that we can see in our background image. For the testing of this method, we used first a single-shot object detector, a state-of-the-art one. Actually, it is SSD, single-shot multibox detector, with the MobileNet V2 backbone. We used this and we trained this model on 3 object classes: the target gate, which is the gate facing the camera that is the closest, and then forward gates and backward gates. So you can see on the video on the right that it works quite reliably, except when the gate is too close to the camera. It is not visible enough and the network has trouble detecting it. And for this problem, we created another CNN, a custom one this time, with a really simple architecture composed of several convolutional blocks and a few fully connected dense layers. This CNN regresses the distance to the gate. For that, we generated a second dataset, but with different annotations this time. And we did a little bit of data preparation before training the model. For instance, we converted the base image to grayscale, and then we cropped the region of interest and zeroed out the rest of the image. So we can get rid of the image features that we don't need, such as the color information, and also give emphasis on the spatial features and the scale features. And these gave us pretty good results that we then use to know when we are close enough to the gate to cross it. So to evaluate the complete method in real-world condition and in a racing environment, we chose the Intel Aero drone for our experimental platform. And our strategy is quite simple. It consists of aligning the gate center of the target gate that we detected with the center of the image using a PID controller. So we used our 2 networks, the gate detector, which is a simple object detector to detect the target gate and obtain the center of the gate in image coordinates. And we used the distance estimator to know when we are close enough to decide to cross it. All this information is used by the state machine to do all the decision making, and it uses the PID controller to send velocity commands to the low-level controller. The only sensors that we have used is a monocular RGB camera and a vertical LiDAR to know when we have crossed the gate and switched state. For the experimental setup, we have used the same arena as we used to collect the data, because we can use the motion capture system to evaluate the flight of our drone and to know if we cross the gate at its center, for example. We have created several gates of different widths and different heights, and we used cardboard cutouts that are not seen on this image to give a little more sport feel to it. The video on the left shows our different runs of the system. The drone always starts on the bottom, on the ground, and it takes off at 2 meters of height before deciding to look for the gate and then start aligning with it. The flight speed is set at 2 meters per second, and the drone starts at 3 different positions relative to the target gate. You can see on the image that there are other gates in the background, but they're turned facing backward so that the perception block doesn't target them. As we can see on the video and on the diagrams and the figures on the right, the system is able to cross gates at different flying speeds and initial positions with quite a high success rate, and it consistently crosses the gate in the center of it. To conclude, we have developed a novel dataset generation method, and we are able to realistically generate semi-synthetic images at will. This allowed us to train two different CNNs, one for the detection problem and the other for the regression problem, that show proof of the viability of this method. We also designed a complete autonomous flight system to put to the test our whole pipeline, and promising results were obtained. But for future work, we have planned to remove the need for motion capture systems so that we could apply this method to outdoor environments as well. It would be great to improve the control strategy and to add path planning, because right now the system is only able to cross one gate at a time and start looking for the next closest gate. Thank you for watching.